Black holes will eat whenever there is something for them to grasp in their gravitational clutches. The rate they eat depends on how much material can be captured, which means that, just like people, black holes will eat at different rates and at different times. Sometimes you're having an off day, you don't really want anything to eat, or you may be fasting. Yet on high days and holidays, you may overindulge, eating way more than normal. Although black holes don't really choose their food in the same way we do, they can go through cycles of feast or famine, or anything in between. This change in food intake can result in a change in the strength of the different components of the spectrum of the black hole. So what are these changes and what do they look like? If we take another look at our spectrum of an accreting stellar mass black hole, we can see the different components that we've learned about. We have an accretion disk, a corona, and a jet. If we zoom in on this plot to take a look at just the X-ray band, we can see the two X-ray components more clearly. Here we see that the disk is dominating the emission from the black hole, while the corona slopes gently upwards as we move to shorter wavelengths. Now let's look at some real data taken from our old friend Cygnus X1 and see how this compares. If you recall, Cygnus X1 is a black hole binary that contains a stellar mass black hole weighing in at about 15 times the mass of our Sun and a hot blue companion star. If we look at the X-ray spectrum of this source, we can see a large bump at lower X-ray energies, which is explained by the thermal emission from the accretion disk. The bump's long tail, as it is sometimes referred to, extends to higher photon frequencies or shorter wavelengths. The spectrum looks pretty similar to what we were expecting to see. So what was seen during a different observation of Cygnus X1? Well, something quite different. The blue line has a steeper incline, increasing towards higher energies, and seems to peak in the same area of the plot that we would expect to see the corona. So what's happening here? The truth is, scientists haven't collected enough information to know for sure. This is the type of change that drives astronomers to continue investigating these sources, and for them to ask the questions about what could be causing these changes. Our view of black holes changes over time. Sometimes we can get more emission from the disk, while at other times we can receive more photons from the corona. What physical mechanism could be driving this? One of the leading theories is that the change in the amount of food available to a black hole changes the portion sizes of each component. As the amount of food from, say, a companion star changes, the serving size of the disk could decrease while the corona increases. When we look back at the image we built up during Module 8, we saw the disk extending towards the black hole with the corona that could either be explained by the lamppost model or the sandwich model, with light coming from both the corona and the disk as material moves in towards the black hole. If our portion sizes are changing, how does this affect the view of the system, assuming we could go for a visit? Well, let's simplify things to start off with. We're going to stick with sandwich model for the rest of this video, given our love of food. Here, the filling, or our disk, takes up a lot of our view. So we could say it's dominating the picture. In fact, it's stretching all the way down to the innermost stable circular orbit, or ISCO. This is when the disk is at its brightest. It can be so bright, in fact, that the emission from the accretion disk can be the brightest component in the optical band of the spectrum. When this is the case, we would not be able to see what kind of star the black hole is consuming. The bread of our sandwich is almost missing. The corona is so thin and wispy that we don't really receive too many photons from it. The sketch we see here of our spectrum matches quite closely to the spectrum of Cygnus X1 shown in red. Astronomers call this the high state. This name is historical as it comes from the early days of X-ray astronomy. It's known as the high state because it's a higher luminosity. It was the brighter option. Have we mentioned astronomers like simple names? Following that line of thought, the next state I would like to mention is the low state. So named because it's the fainter one. When black holes are in the low state, the sandwich is switched. Where the disk may feel thin, sort of stretched, like too little butter scraped over too much bread. In the low state, the innermost part of the disk is not at the ISCO. It is found some distance away. We learned earlier that we can think of the disk as being made up of a series of many rings. As we progress inwards through the disk, the temperature of each ring increases. This means that the highest temperature we detect from the disk, also known as the peak temperature, would come from the innermost ring of the disk. In the low state, the inner disk is further away from the black hole. This means that the disk spectrum is cooler and so shifted to the left of our plot. We also find the disk is fainter. So faint, in fact, that this is a great time to check out the companion stars of the black hole. Here we have a lot more bread for our sandwich, with the corona dominating the innermost region around the black hole. With this increase in corona, we receive more photons, as it begins to dominate the X-ray spectrum. This is more akin to the spectrum of Cygnus X1, shown here in blue. These two strikingly different views of the same source, built with the same components. But what about the jet? It turns out, although the disk and corona appear to be permanent features, the jet is not. The jet is strongly associated with the low state. Although astronomers don't fully understand how jets are launched, they have found strong ties between the emission seen in X-rays and the radio emission. By combining information relating to the brightness of these electromagnetic bands, you can obtain estimates on the mass of the central black hole. In order to investigate the high state and low state that had been seen in the emission from stellar mass black holes in binary systems, astronomers continued to make observations of these sources. Over time, they found that black holes could get even brighter, which seemed to correlate with a change in the shape of the spectrum. This called for a new accretion state, known as the very high state. If we break this model apart to build a picture of what we would find there is both lots of disk, possibly extending to the ISCO, and a lot of corona. In this case, we seem to have a sandwich that is more balanced, with both a good amount of filling and bread. Tasty. During the very high state, it's possible to see the jet, although it's not always present. We have explored 3 black hole brightness states. In addition, some astronomers are lobbying for a 4th intermediate state that seems to live somewhere between the high and low states we've already discussed. But how do these states relate to one another? By looking many times at multiple sources, astronomers have seen cycles emerging within many systems. Cycles start with black holes that are either off or in the low state. When a feeding frenzy occurs, the black hole will rapidly brighten. This can take as little as hours to occur. Given the rapid rise, many times this can be missed by observers. After the low state, the black hole transitions to the high state and possibly even the very high state, or beyond. Black holes can hang out in the high state for a while, depending on their food source, with some sources, like GRS 1915 plus 105, seeming to stay in this state for decades. Towards the end of their dinner sitting, they slowly return back to the low state before fading away. These cycles are called outbursts. These outbursting cycles can also take place in supermassive black holes, but over much longer timescales, with outbursts lasting centuries. Too long for an astronomer to observe in their lifetime.